check the recording. It is recording. I guess I can bump up the mic just a little bit. Is that too much? Wrong dial. Is that too much? No, that's too much. Is that okay?
Yeah.
All right. I used to have a professor who used a microphone in class, and he'll be sitting the entire time like this. And this is back in the old days when we have overhead projectors, like the old style overhead projectors. And he had everything prepared. So he'd flip on the slide and then just drone and talk about stuff. And then at the same time, he would use a pen. That's how he not writing, he would just make circles around the paper when he's talking. That's kind of his own thing. But you can kind of imagine what happens when that pencil gets magnified by the overhead projector. So it will be like going full circles, full screen, on the projection screen. And half the class will be asleep within 15 minutes of that class. And that's why when I turn on the microphone, I kind of have to keep that in mind and make sure that I don't put you guys to sleep like that. Okay, but these days it's different because back in those days we did not have computers in front of us, we did not have cell phones, we did not have the electronics to keep us distracted otherwise. So we had to focus on the droning, and that's what put us to sleep. You guys don't have you guys have all kinds of distraction to keep you awake. The question is, are you absorbing the material in this class? All right, so let's go ahead and get started again with pointers and addresses. Are there any questions from last time? I think that was a question about the ampersand versus the asterisk, right? Is that kind of the question?
Yes.
Okay, so let's go ahead and take a look at those and figure out what they actually do. Now in this class we use a GDB a lot, okay, and that's because in GDB we can actually do things interactively. So instead of me explaining the concepts in a kind of dry way, we can actually go ahead and inquire in GDB. Okay, what are we looking at here? So what I'll do is I'm going to write an extremely simple program, just like that. We'll just say x equals to 20. Return 0. That's it. That's the entire program. And hopefully at this point in time, everybody should feel comfortable with a program like this, understand what it does, or how little it does actually in this case. And I'll just ask you one question. What is x? It's a variable, and as any variable in C and C++, it has an address. It also has a type. Okay, the type is it's an integer. Okay, and what can x store? What kind of value can it store? Integer values. And what can we do with integers? We can do math with them. Very good. Okay, so we can add, subtract, multiply, divide. We can do bitwise operations, right? We can use bitwise OR, bitwise AND, bitwise NOT, bitwise exclusive OR. Okay, so there are all of these things we can do with integers. Okay, very good. All right, so the next thing we'll do is actually to compile this program without using the ampersand or the asterisk operator. The address of is ampersand, and then the reference is the asterisk. Okay, so we'll go ahead and save the program just the way it is. Okay, compile with -G so we can run the debugger. And then the next step, we'll go ahead and link the program. And then we can just go ahead and test the program. Now obviously this program doesn't do a whole lot of interesting stuff, so what we'll do is we'll just put a breakpoint on line 5, run the program so that at least at this point we have variable x to examine. If you're not running the program, if the program is not in execution, you cannot look at the variables. Okay, so it's only when the program is running, in this case because x is a local variable, it can only exist in the subroutine, in this case main, only when the subroutine is invoked. Now because main is the entry point of the entire program, it has to be active. It has to be invoked. All right, so we'll go ahead and single step, and not surprisingly, we know what x is. Okay, because when we ask, hey, give me the value of x, it has a value of 20 after the assignment statement. No big deal, right? Okay, now let's go ahead and ask what is ampersand x. Go ahead.
Just a functional question for main. When you start a program in any operating system, is it really just directly starting main, or is it going to go through a couple steps before that?
There are a few steps before it calls main. It has to set up the stack. It has to set up the, if we had any global variables, it has to set it up too. If we had any static initialized variable, it has to set up those as well. Now, since in this program we do not have any global variables nor anything like that, so the entry point code doesn't really have much to do. But there is entry point code before main is called that has to be active first.
Is the entry point code considered high level or low level?
It's low level. So in most cases, your program written in C or C++ does not need to be aware of that. Okay, those are very good questions. All right, so we know what x is. So the next question is, tell me what is the address of x, okay? Because ampersand x is basically saying what is the address of x. Now, an address is nothing more than an integer corresponding to the first byte location in memory that corresponds to x as a variable. Every variable has to be stored in memory. Okay, so in this case, x is a local variable. It has to be stored in memory, and as a result, it has an address in memory. So this ampersand operator, which are otherwise known as the address of operator, is basically saying, okay, what is the address of x? So in this case, it doesn't tell us anything about the value of x. It only tells us what is the address of x. Now, when we display addresses, even though it is an integer, it does not usually use decimal numbers. In other words, when we display an address, in GDB and in most other debuggers, it will use the base 16 representation. That's because base 10 doesn't really help, and it has a lot more digits. So base 16 is much more compact, and since we're not going to do a whole lot of manual calculations, it's okay to be in base 16. Is that okay? So address of is basically saying, okay, we have a variable. I'm not interested in the value. I want to know where it is. So the next question is, what is asterisk? Okay, if I do something like this, what is it doing? Well, based on the grouping, because of the parentheses, we know that ampersand applies first. In other words, we are saying, okay, let's go ahead and find what is the address of x. But what are we doing with the address of x? In other words, what is the asterisk operator doing? The asterisk operator, because this is a unary operator, asterisk does not mean multiplication anymore. Now it means dereference. Dereference is basically taking an address and say, okay, give me an address. Okay, here's an address. What am I going to do with the address? I go to that location and find out what is the value at that location. So it does the reverse of address of. Is that okay? So if I do this recurrent, okay, let's run it. So it displays 20. Now, obviously, this is completely redundant and unnecessary because printx would have given me exactly the same thing. But that's okay because the point is to illustrate that asterisk and ampersand are exact opposite. They undo or they reverse the operation of each other. So that means if I do something like this, it will still give us 20. Because every time we have an ampersand, it is asking, oh, you're giving me the content, the value. I'm not interested in the value. I'm interested in where it is. So you're basically just keep doing, okay, where's the address of, and then go to that address. What is the address of? Go to that address. And that's why they kind of undo each other, and you can stack this up as many times as you want, and they will still do the same thing. Does that answer the question?
Yeah,
okay. Sort of.
In the lab on number 6, you have like set var and then asterisk, int asterisk, and then outside of that you have the address of x.
Yeah. Okay.
And
so
I didn't understand really what the asterisk did at that point, but now now I understand.
Okay. Excellent. Excellent. All right. So are there any other questions regarding addresses? Yep.
The question is, whenever you are using the value of a variable, is it basically just implicitly saying the dereference of this address?
Which operator again?
Just
the ampersand?
with any given operator on a variable, when it's taking the value from that?
Correct. When you apply like multiplication, okay, and you only refer to the variable itself, you're always referring to the value of a variable.
But I guess on the assembly level, is it literally just saying, is it the same process as having dereferenced?
At the lowest level, the compiler generates the code to find the address first, because you cannot get to the value unless you have the address, right? So from our perspective, the address of is like, oh, we are doing one more step. But from the compiler's perspective, it always knows the address first. But when you refer to a variable without the ampersand, then it is only referring to the value of that variable and not the address of. So I understand the question, but it's from the perspective of the compiler, referring to the value is the default because that's how we work, that's how we want to use variables. But in order to make it work, the compiler actually has to find the address first, and it will implicitly dereference the address to find the value.
It doesn't matter because it has to know anyways.
Correct. That is correct. And that's why the ampersand operator in all cases does not actually make your program go any slower, because it is actually one fewer step compared to having to access the value of the variable. Yep. Mm-hmm.
Why do you return a decimal number instead of a binary or hex number?
You mean for the address?
Well, when you did the dereferencing of the address, why did it return a decimal number instead of binary or hex?
When I did a dereference?
Yeah.
You mean
like how did it know
this
the
one?
type? Yeah.
Because this is a default of print. Because print has a default. If you say help print, it will say that well, it says right here it defers the discussion to the X command, but D or signed decimal representation is the default of how you want to print something. Because that's, in most cases, people want to look at signed integer values in base 10.
So if you were to try and print dereference a variable that was, say, like a character or something like that, it would still print it as a base 10 number?
That is correct.
Okay.
Yeah. But if you're printing a variable that has a char type, then it will print not only the value, but also it will print the actual character that the ASCII code is representing.
And so it checks the type
Yep.
stored for it when you
Yep.
dereference?
Yep. Yep. GDB is actually pretty smart. When we use the -G option in G++, that option makes G++ include not only the symbolic names and many other things, but it also includes type information of variables in your program into the object file. The object file is then linked into the executable, which means the executable also has that information, and GDB extracts that information, and that's why it understands what X is. It has a type of integer and so on.
What would happen if we tried doing all this without adding -G when we were compiling?
Then it would give you something, it would complain and say it doesn't know what X is.
Okay.
So let's go ahead and do that once, okay? Because I do want to show you guys, what if you forget about -G, and you do everything else the same, you still link, and then you go to GDB test. Now, that by itself is okay. It doesn't say, oh, I cannot do this. But the last line does give you some indication, because when it tries to read symbols from test, it complains and say, hey, no debugging symbols found. So that means when you do it the L, it can no longer see the source file because there's no references back to the source file. Now, it doesn't mean that you cannot do a single thing. It simply means that you cannot see the source code corresponding to this program. Okay. Very good questions. Any other questions? No other questions? All right. So if there are no other questions, we'll start to talk about arrays. Okay, so arrays and pointers and accuracies, they're all kind of lumped together in C and C++. In your cisp360 class, okay, first of all, there's no such thing as address. How many people got exposed to the concept of address or address of or pointers in cisp300 or 301? No one. It's not supposed to be there. Okay, so that's a new concept. How many people got exposed to the concept of arrays in cisp300 or 301? All of you should have that exposure from cisp300 or 301. So let's go ahead and kind of examine why we need arrays to begin with. Okay, that should just be a refresher. And then the second thing is, Well, how does that have anything to do with address? Okay, because it seems like those two are separate concepts and should not relate to each other at all. So what we'll do, or what I'll do, is to say, well, let's go ahead and make a program that will find the maximum of a few variables. This used to be a homework assignment for some of my earlier semesters. So we'll start with 2, okay, and then we'll store the result in max as a variable. So if I want to find out which one of these two, x and y, has the maximum value and store it into the variable called max, how would you do it? The ternary operator way is a little bit more cryptic, so I'll do it in a less cryptic way, which basically says if x is greater than y, then we'll do, I have to turn off I have to turn on auto indent so it doesn't, I wouldn't have to, oops, why is it not doing that? Come on, there we go. Okay, so if x is greater than y, then out of the 2 variables, the maximum is x. Otherwise, because I only have 2 variables, the maximum has to be y. Okay. So are there any questions about this code here that finds the maximum between 2 variables and assign that value to max? Any questions about this? Okay, doesn't seem too difficult. I mean, it's doable. Okay, so let's go back to this program and say, well, let's see what happens when we have 3 variables, x, y, and z. Okay, so there are several ways to do this. So I'll go ahead and kind of do it slightly differently. So I'll say if x is greater than or equal to y, then x is certainly one of the candidates of being the maximum. But I don't know the relationship between x and z, because now we can say, well, x can be the maximum, but we don't know anything about z, so it's time to compare x and z to find out which one is the actual maximum, right? So we can say now and say if x is greater than or equal to z, then we have confirmation that x is in fact the maximum. I mean, yeah, so max gets the value of x, otherwise z is the maximum. Okay. On the other hand, with the else case, which simply means y is not less than or equal to x, which means y is actually greater than x. So that means x cannot be the maximum. It can be y, but it can also be z, because by the time I get to this else case here, I do not know a single thing about z just yet. So that's why I have to compare y and z. So I say if y is greater than or equal to z, then y is the maximum. Otherwise, z is the maximum. Okay. There we go. And there we go. All right. This code will work. Okay. It's not a problem. What if I want to add another variable? What if I want to add w? So now we have 4 variables. I want to find the maximum of those 4. Well, I mean, you guys know the general approach. You can make it work, right?
Yeah.
What if I have 400 variables? In fact, I think I should give that to the entire class as one single homework assignment. You guys can work together, because there'll be a lot of typing, right? But you don't want to do that, right? You don't want to do it in this particular approach. That is the reason why we have arrays. Because with the concept of an array, I can use a loop to keep track of the largest value encountered up to that point and just keep updating it. Okay, so let's go ahead and take a look at a program that finds the maximum, but this time it is using arrays. Okay, so we'll go ahead and delete this stuff here. And this time we use arrays. Now when we use arrays, the way to declare an array in C and C++ is to say, okay, this is basically saying A is an array of 20 integers. So the way you read it is kind of like all over the place, because it's saying A is an array of 20 integers. Okay? So to find the maximum of these two 20 integers, I only have to do something like this. So I can say for, and this, you can only do this in C++, but not in C, because in C++ you can declare a variable within a for block. So you can say for int I equals to 0, so you're declaring and initializing at the same time. And we'll also do max equals to a bracket 0. Okay, we use a bracket 0 because all arrays in C and C++, they start with index 0. In some programming languages, you can control what is the starting point, but in C and C++, it has to be 0. So a bracket 0 is the first element of the entire array. Then I say if as long as I is less than 20, because when I becomes 20, it is no longer a valid index into the array. The post operation is just moving I onto the next index. And inside here, now we can say if a bracket I, because I is now controlled by the loop itself, it will keep changing. If that element is greater than max, then I got something to do. Because if I find something, a value that is greater than max, that value becomes the new maximum. Is that okay so far? All right. So if you look at this code here, and I say, well, will this work with 200 items? Well, not exactly, because we have to change the 20 to 200. Change it over here and change it over here. But some of you have been exposed to const, okay? So we can say const int array size equals to 200. So if that is known to be the maximum, then I can refer to array size over here. And guess what? I can also refer to array size over here. So this way, if I need to change the program to handle 2,000 items, I only got one place to change, because I only got to change the constant declaration to 2,000, and then all references to array size will now be updated to 2,000, which is a great idea. Yep.
Would there be a way to have it like shrink or enlarge based on the number of items it needs to have?
Say again?
Would there be a way for it to grow or shrink based on the number of items it needs to have inside?
In C and C++, arrays cannot change size dynamically. So when you declare an array, you have to know how many elements you need. It's not like in other programming languages where you can dynamically change the size of an array. In this case, you have to know what the number of elements by the time you declare the array, which is kind of a restriction, and that's why in other classes in CISP 400 and possibly 430, you will encounter concepts where you have what they call elastic arrays, and you can dynamically change the size of those arrays. Okay, so are there any questions about this algorithm or the rationale of having arrays? Yep, go ahead.
In regards to them not being able to change the size, it doesn't have bounds checking.
It does not have bound checking.
Okay, so if that's the case, then if it goes outside the rest of the actual arrays, what's happening is that it is no longer like keeping track and just overriding actually used.
Yes,
addresses.
it will just be overwriting chunks of memory that does not belong to the array. Now, if if a chunk of memory does not belong to A, what do you think it is used for?
Could be anything. Might be
Could
something
be
important.
exactly. It could be anything, and it is always something that is important. Because the compiler is not going to allocate memory and just say, we'll just go ahead and waste 30,000 bytes here just for no particular reason. So every byte counts in memory. So when you're overwriting an area that is not a part of the variable or array that you want to overwrite, you're overwriting something else. Now, depending on what you're overwriting, your program may not crash right away. Okay, you can end up changing the value of another variable in the process. Okay, so we'll examine that today. Okay, what is an array in C and C++, and why does it have anything to do with addresses and pointers and stuff like that? Because those two concepts do not appear to be related at all, but they are actually very much related. Okay, are there any questions? Yep, go ahead.
So in this example, we didn't need to sort out the array, so that at least you just have to put the code like that, and then to just pull out the maximum number, or you need to sort out the array first before you do it.
In this case, you do not have to sort the array. This array does not need to be sorted, because it will find the maximum regardless. Right, if the array is already sorted, then I don't need to search, right? I just go to either the first item or the last item, depending on how the array is sorted. Yep. Mm-hmm.
So in regards to the array was declared, so it's when you declare an array and have a size for it,
Yep.
what's happening is it's only creating, I guess, clean variables for the number of addresses that would be needed for that size. size?
When you look at int a open bracket array size, all you need to do is All that really is doing is to tell the compiler, oh, reserve enough space for this many integers, okay? But when we're actually indexing, okay, let me just point out where we are talking about here. I'll address that. So when we're actually indexing, then you're basically saying, oh, let's go ahead and access, a certain element of this array. But by this time, the compiler only knows where it starts. It has no idea where the array ends. So if you supply an I that is out of range, it will keep going. It will actually pretend and say, oh, well, you want to access 2001? That's okay, I know where it is. But is it really a part of the array? The answer is no. So you are accessing an array that is not a part of an array when the index is out of bound. Yep.
On writing outside the array, just thinking back to the other stuff we had to do with pointers and things, if you're trying to write to something not like allocated to the specific process, would it get you an error message from
Yes.
the OS?
That is correct. It will give you an error if you try to access a memory location that is not allocated. So we are talking about stuff that is allocated, but those are not variables, or they could be variables that belong to somebody else. Could be another variable. Okay, so we'll take a look at those today. Okay, we'll have a lot of fun with how memory is allocated, how variables are allocated, and why arrays are really nothing more than just addresses. Okay, so we'll take a look at all of that today. All right, so this program is kind of interesting, but it's kind of boring also at the same time. So what I'll do is I'm going to save this program, but we'll go back to a test program, just like test.cpp, except this time we make it a lot more complicated, like that. Okay, well, if you guys want, we can say y equals to 23, z equals to, I don't know, 42. 42 is always a good number to use. Okay, so we have a much more complicated program now. Instead of having one single variable that we don't really use it for anything, now we have 3 variables that we don't use it for anything. Okay, we just put a value into those things and say, okay, that's it. So what am I going to do with this is to go illustrate the concepts in GDB. Okay, so once again, we are relying on GDB to understand these concepts. So G++ -G, that's important. And then we link the program. And then we go into GDB, list the program, put a breakpoint on line 8, and run the program. We say print X, print Y, print Z, nothing interesting at all, okay? Because these variables simply have the values that they're supposed to have. So what is the whole point of this exercise? Let's look at the addresses of these guys, right? So we can say print $x, okay? Print $y, print $z. Okay, well, some kind of gibberish, hexadecimal thingy, okay? But do you see a pattern? Is there a pattern to the addresses of these 3 variables? What if I tell you each variable is a 32-bit integer and every 32-bit integer requires 4 bytes? Would that make any difference in terms of trying to identify a pattern in the addresses?
Yeah.
Okay, so what do you notice?
I noticed that you got 0xbFFF 3F4 and then 3F0.
And those are off by
4 bits.
4 bytes, okay? And F0 versus EC is also off by 4 bytes, okay? Because remember, C represents the value of 12. So what happens when you subtract 12 from 0? Oh, well, we don't know how to do subtraction in base 16 when the first number is less than the second number. So what do? You borrow, right? So you borrow 1 from the next digit. But what are you borrowing from? What is this F representing? It's representing the number of 16s, right? So you borrow a 16 and then you subtract a 12 from the 16, what do you get? You get a value of 4, okay? So that means the address of Z is 4 bytes before Y, and then the address of Y is 4 bytes before X. Okay. Is that suspicious, a little bit suspicious to you? They're consecutive? Okay. So I'm going to show you one really tricky thing now, because what I'll do is I'm going to say, oh, give me the address of Z, okay, put in parentheses, okay. Now, obviously, that doesn't really do a single thing, because parentheses are really only used for grouping purposes. So it will still give me exactly the same thing, but what is the type of this BFFF3EC? What is the type of it?
That should be an integer, right?
It's not an integer, it is the something of an integer.
That's the address.
Isn't the address of an integer. Okay, very good. So now I can use the array operator, bracket 0. What? There's no array in this entire program. Any address of an integer can be seen as an array. That is the whole thing about pointers in arrays in C and C++. Any address can be seen as an array. That's the beginning of an entire array. Is that okay?
Is it specific to each variable?
If you extract the address of any variable, it can be seen as an array. Now, whether it really is an array or not is a whole different question. Okay? That is the whole thing about C and C++. Once you know the address of something, it can be treated as an array. You first, and then you. Okay, go ahead.
You specify of an int. What happens if it's not an integer value or an integer type, or if you typecast something that's not an integer into being an integer? I guess that's two different questions.
Well, if it's an address of blah blah blah, then it can be seen as an array of blah blah blah.
Okay, what if you mix in like two different types of values?
You
into an
cannot.
array?
Then it will be seen as such.
Okay, so it'd be like typecasting something into being an integer.
It's not exactly typecasting either. You're basically fooling the compiler and say, I want to look at these things as this, but it's not typecasting either. Typecasting would actually do it would extend the width or contract the width of the value, but when you use this method, it does not do that. Yep, go ahead.
Okay, so say print a random integer value and then say go to the second element in the array. Is it just going to use the basis of the size of an integer type to move forward?
Yes, that is basically all it does. Okay, so if I look at the address of Z, yeah, go ahead.
Sorry.
No, that's fine. Go ahead.
So just to kind of use your array program as an example, you had the array set for like 2000.
Mm-hmm.
Because there's a 0, it would technically be like 2001, right?
No, it actually, okay, the 2000 inside the square brackets, when you declare the variable, that sets how many elements you want in the array, which basically means the valid index will go from 0 to 1999.
Okay. Alright, that makes sense. Never mind. Alright.
Okay, all right. Okay, so let's take a look at this syntax here. Let's take a look at this expression here. We'll evaluate this thing first, okay, because it's inside the round parentheses. This is the address of Z. Then we'll look at the expression inside the square brackets. Oh, that's just 0, right? 0 is 0 all the time. So when we apply the square bracket operator, which is array indexing, this is called the indexing operator, on the address of Z, it is basically saying the address of Z is an address. Okay, if I treat that address as the starting point of an entire array, I want the first one now, because square bracket and then a 0 and then close square bracket is basically saying I want to get the first element of this array. And what do you think is going to print in this case?
42.
It's whatever Z has, which is 42. Okay, so let's double check and make sure that is in fact 42. Okay, that's 42. But that's not too bad, okay? Because bracket 0 close bracket is kind of the same thing as asterisk. It's kind of like just dereferencing the address, okay? Because it's just going to that place and say, oh, let's pretend this is the starting point of an entire array. What is the first element of the entire array? It's whatever is there, right? But the question is, what if I change this to a 1? Okay, so let me display this on the whiteboard first, okay? Because I do want to show you what it looks like. When I draw a memory, I always draw it where the higher portion, upper portion is the higher address, and the lower portion is the lower address. So we are basically looking at x, y, and z in memory. X is a variable, it has 4 bytes. Y is a variable, it has 4 bytes. And z is a variable, it has 4 bytes. Is that okay so far? We know the starting point of z is BFFF, blah, 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 and then EC is the end. We know y ends with F0. We know x, or the address of x, ends with F4. Is that okay? The address of operator will give us the actual address. But in C and C++, the address of anything can be considered as an array. Now, when you look at it as an array, okay, when you look at the address of Z as an array, then you go like, oh, what is the first item of this entire array? Well, that's just Z itself. What is the second item of this entire array? It's whatever is adjacent to Z right next to it. What would that be?
Y.
It's Y, exactly. And what would be the third element of this array? Is actually X. Yep.
If in the program we had Z was a standard int, the 32 bytes, and then we typecast Y and X as 16-byte or 16-bit
Okay.
integers, would it read YX as a single integer value considering
If you
Z
try
was
to do this
32
trick,
bits?
yes.
Okay.
Yep. Well, it depends on how it makes use of stack space too. For efficiency purposes, even if you need a 16-bit integer, it will still allocate 32 bits.
Okay.
So that trick may or may not work. It depends on whether the compiler is set to save memory or whether it's configured to maximize performance. Okay, but let's just focus on this one. So when I print this out, it actually prints the value of y. And if I bump the 1 up to 2, it actually prints the value of x. Okay, this is why I said earlier the concept of an address and the concept of an array is all the same in C and C++. Yep.
So it's just traversing the address instead of the actual value, I guess you could say.
There's no such thing as the value of an entire array. That is also a good point. Okay, if you declare A to be an array of 20 elements, okay, 20 integers, you cannot refer to A by itself as a value because you cannot refer to all 20 values at the same time.
Right, but I'm saying like, I don't know if I can really word this correctly.
No, go ahead, try.
So it's just, okay, well, it's just going to traverse the address regardless of whatever the variable is set to.
That is correct.
Okay.
That is correct. Which basically means, you know, the indexing operator is always just basically saying in this particular case, let's just focus on one. Okay. In this case, we're extracting the address of Z. We know that part, right? You know, ampersand Z is just the address of variable Z. But this part is saying I want to access the third item, assuming that address is an array. Okay, so it would just basically say, okay, let's figure out how many bytes each element is going to consume. Okay, it's 4 because we know this is. How do we know it's 4? How do we know it's going to take up 4 bytes for each element? What is the type of ampersand Z?
So integer and a 32-bit.
It's an integer pointer, right? Okay. So what does it point to? What does the address of Z points to? Points to an integer. An integer uses 4 bytes, right? So assuming this is an array of integers, this ampersand Z bracket 4 is going to say, oh, let's look at not where ampersand Z is, but 8 bytes after that. But who turns out to be 8 bytes after the address of Z? Variable X. Is that okay? Sort of?
So you're picking Z as the starting point essentially.
That's all it is.
Okay.
The address of Z is just treated as a starting point, and that's all it is, okay? But we have no idea where it ends because it really is not an array. So if I do something like this, it will do something, it will print something. If I do something like this, it will print something, except those are not actual variables that we have declared. It's not saying they're not important. They are very important. Okay, if you overwrite these locations, your program will crash And in many cases, it will crash in a very strange way.
So if you were to do like a set var, and then ampersand z4, and
It
then
will go ahead and change 4 bytes somewhere in memory, but it does not correspond to any one of the variables that you have actually used or declared, which means it's going to trash something else.
Right, that's like what he was saying about the memory, because it's not checked, it doesn't check itself, essentially.
It has no bound checking, exactly. It has no bound checking. It is just saying, oh, I'm assuming that you, the programmer, knows what you're doing. If you tell me to treat this as an array, as the beginning of an array, I'll do that. If you tell me to go to the 20th element of this array, I'll do that. Not a problem. What if that thing is really not an array, or the array does not have 20 items? It doesn't care. Okay, the code that actually runs does not care. It does not know, and it doesn't care. So what ends up is you will be corrupting something. So if I say, set var ampersand z bracket 4 equals to something, it would actually go ahead and change that. Okay, but what is the effect of changing that location? Then it depends on what it is. Okay, it can be the return address, it can be the frame pointer, it can be a variable of another function. Okay, now all of those things you will see in CISP 310 in assembly language programming, because that's the focus of that class. But in this class, all I'm going to say is this is bad. Okay, it is really, really bad because it is going to overwrite something. Okay, so let's go ahead and work with a program similar to this one, except this time it actually does have an array. So we'll go ahead and say int a bracket, I don't know, 4 is good. Okay, so now we have variables a, x, y, z, and also the array a. Okay, and inside the program itself, because we say, well, maybe the compiler is smarter than GDB, and when I do something that's not smart, it will catch me and say, hey, this is not good. So we'll go ahead and say, what is a bracket, and change a bracket 4 to a particular value. So let's make it very distinct. Let's say 71. Okay, first of all, I'm hoping all of you can see that this program has a flaw already. Okay, because a bracket 4 does not refer to the 4th element of the array. It actually refers to the 5th element of the array, because the first element has an index of 0. So the first 4 elements would have the indexes of 0, 1, 2, 3. So a bracket 4 is already referring to something that is not a part of A. But based on what we saw earlier, we kind of know, I have a strong suspicion that this is going to be a bracket 4 is one of the 3 variables. Okay, so let's go ahead and see whether that really is the case or not. Okay, G++. Oh, I have to spell it out because there are 2 C++ commands. Test.cpp, and then we'll go ahead and link it. So list the program, and we'll put a breakpoint on line 9. Okay, there we go. We run the program. All right. So we'll do the same thing. What is the address of X, address of Y, address of Z? Hey, those have not changed from last time. So where do you think A is? In other words, if I were to say, hey, tell me what is A, where A is located. Okay, it's some kind of mumbo jumbo location. Well, it's not just mumbo jumbo, is it?
No.
How does it relate to the address of Z? How many bytes are between those 2 addresses? 16. Exactly, because you can see that the number of ones, they're both C's, right? But the number of 16, one is E, the other one is D. You don't even need to know that E represents 14 and D represents 13, because they're just off by 1. But because it is the second least significant digit, off by 1 means that they're off by 16 as a value. Yep.
So it means that when you want to change like any number, then put like a W. Then when you initialize W, they need to just go directly to that address.
It depends on how you declare W. If you declare W before X, then W has the higher address. But that's also compiler dependent. Okay, some compiler may decide to arrange things this way. Other compilers can arrange things slightly differently. Okay. So now the question is, the big question is, well, let's just single step this program. Okay. So I'm going to single step this program, and the question is, what really is changed to 71? Because array A only has 4 elements, and I'm changing the 5th element to 71. It's trashing the location of somebody else for sure, but in this particular program, based on what we can see as the addresses, who is getting the value of 71? Who's getting overwritten by 71?
Z.
Yep, C is getting overwritten. So let's double check, confirm that. That is in fact the case. That is how arrays are organized, or how arrays are used in C and C++. It is not the best way. It is not safe at all. People can get themselves into trouble all day long using arrays and addresses. And that's why when you guys write any programs using arrays, you have to be extra careful. Is that okay so far? Okay. So the next thing I will do is not to talk about the concept anymore, but I will talk about, I'll illustrate what happens when you try to overwrite an array to the point where it does not belong to the array anymore. Okay, what would be the possible symptoms of a program when you do something like that? Okay, there are many ways your program can misbehave. I can only show you certain ways. Okay. All right, so let's go ahead and write a very simple program. I'll just call that crash, because that's the entire purpose of this program. It's going to crash. Okay, we'll write a void function. A void function means it does not return any particular value. It does not take any parameters either, because this whole thing is supposed to just crash. So we'll say int a, and a interestingly only has 1 element. Okay, it's an array, but this array only has 1 element, because I don't really care about what is in A. I want to use A to crash somebody else. That's all I want to do. So I'm going to say A bracket 1. Okay, so I'll trash the location right before A and see what happens when that location is trashed and becomes 0. Then we have the usual main. And main doesn't do a single thing except to invoke F, and then we'll have a regular return 0. Okay? First of all, I want everybody to understand this program has a problem. Okay? Because array A in function F only has 1 element. But when we use square bracket 1 over here, we are actually accessing the 2nd element of A, not the 1st element. It has 1 element, so the 1st element is fine. But since it only has 1 element, there's no such thing as the 2nd element. But I am saying, let's pretend there is, okay, and override that location with 0. Okay? So the first thing we want to do is to say, okay, is this going to crash the program? And I will shortcut this. Some of you may have known this trick already. You can shortcut it by using a -o on the same line as a -g, but you have to supply the CPP file instead of the .o file. And then we have a program to debug. Well, let's run it by itself first. Doesn't seem to be a problem. And if I run it in GDB, I don't think it's going to be a problem either. Okay, run the program, and it says it exited normally, which means everything is good. Okay, so what that tells me is those 4 bytes, is not actually used, by anyone. So occasionally you might have, locations like that. So now I move on to the 2nd location. Yep.
Well, based on the earlier example, didn't it actually overwrite the return value with 0?
No, it's it has to be 8 bytes after that, then it becomes the return address.
8 bytes after the A?
After the last spot of local variables. So yes, 8 bytes after A, which is what we are trashing now.
Okay.
Yep. So we're going to do the same thing, recompile the program, and then we'll run crash again. This time it does crash. Okay? Now let's just take a look at the program again. That seems kind of obvious. Okay, we have an array A, it has only 1 element, and we're trying to access the 3rd element in this case. So it's pretty kind of spelled out in this case. But what if this statement is in a loop and a bracket 2 is just a bracket I or some kind of expression that turns out to end up with a value that has a value of 2? It's not that easy to catch anymore, because now you have to analyze the actual loop and how it changes the variable involved in an expression so that the expression would actually exceed the range. Are you guys kind of getting the general idea of why this is hard to spot in an actual program? In this case, yes, it is spelled out to you and say, yes, we are trashing memory, but in an actual program, it can get very difficult to locate. Okay. But what if your program is crashing because of a reason like that? Well, you don't just give up, okay? What do? What would TAC do?
Debug it.
Debug it, and how do we debug a program? Gdb, exactly. So we go to Gdb, and if you don't want to do a single thing and just say, okay, I don't want to do a single thing unless I have some information to go with, that's fine. Just run it. It will crash the same way. But what is it telling you? It tells you that it crashed because of a segmentation fault, but at the same time, it gives you this number, 0x, blah, 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 in question mark, open paren, close paren. What does that mean? It means it's trying to continue execution at location 0. There's only one reason, or this is the primary reason why it wants to continue execution at location 0, is because the return address is trashed. Okay, so that's not really too bad, because the crash is pretty much immediate, in the subroutine that is causing the problem itself. What if we trash something else? Okay, so let's start to look at something here. We have a local variable in main, and before we call f, we say x equals to 42, and in here now we trash it in a different way. Okay, so we'll say trash the fourth element of A, which means we're accessing something that's 12 bytes after the end of the array. Okay, the program before is trashing something that's 8 bytes beyond the end. This time is 12 bytes beyond the end. Okay. So we'll go ahead and run the program. Go ahead and run it. Whoops, compile first. Run the program, and it doesn't seem to crash at all. Okay, but does it actually do something that's really funky? That's the question. So what we'll do is we'll put a breakpoint on line 13 after f returns, run the program, and we say print x. X is still 42, so it didn't trash that either. Okay, let me try to remember what locations are where, because I want to cause this to trash in a certain way, to crash in a certain way. So return address is there. Frame pointer. Let's go ahead and change the program a little bit. So we're extending the overwriting location. Now you're further and further away from the end of the array itself. It doesn't crash, but I think this one will actually do something that's really, really funny. So put a breakpoint on line 13, run the program, and if I print x, what should I get? I should get 42, right? Because x is a local variable of main, and nobody, as a local variable, nobody should have access to a local variable like this. F certainly should not have access to local variable x. Oh, it did. It didn't crash this one. It did not overwrite it. Okay. Well, you know what? I'm going to cheat here, because I want this program to overwrite mains, the local variable x of main from f. Okay. So I'm going to cheat here by putting a breakpoint first, and I want to put a breakpoint on line 11 as well. Rerun the program, and some of you know what I'm planning to do already. I say, tell me where is x. Okay, in main, continue execution. Now it is in f, and then I'll say, hey, tell me where is a, or tell me where is a, and it tells me it is at 3DC. So if I want to go through, if I want to use array, quote unquote, array A to overwrite local variable x, what is the index that I need in order to accomplish that? What kind of math will be involved here?
Can you
Okay.
repeat the question?
Sorry?
Can you repeat the question?
Okay, the question is, I want this program to exhibit a very odd symptom. Okay, I want function f to use quote unquote its own array A to overwrite local variable x of main. Because that should not have been possible otherwise. Is that okay? So the question now is, what is the that's the what. Okay. So now the question is how? How can I do that? Yep.
20, would it be 24 or 20? Because it'd be 24 after that. So 23?
Well,
No.
I'm lazy, so I'm going to use Gdb to do the calculation. Okay, so the first thing I do is to calculate how many bytes are between the array A of function f and local variable x of main. Okay, but they're all in memory, right? I mean, I can surely look at those integers and say, just give me the difference between those locations. Is that making any sense? Sort of. Okay. So press the enter key, because after all, BFFF F3 F4 is a hexadecimal number. It is a number, it's an integer. BFFF F3 DC is also just a number, it's just in base 16, and we are not used to subtraction in base 16, and that's why we don't get 24 right away. It's just not it's not natural to us. For those of you who can do hexadecimal numbers, it's actually not too bad, because what you see is 4 minus C is 8. Okay, because C represents 12, right? So how do you subtract 12 from 4? You cannot. So you have to borrow first. But every time you borrow in base 16, you're borrowing 16. So 4 plus 16 is 20. 20 minus C is 20 minus 12 is 8. But because you already borrow, the F becomes an E, right? E minus D, well, that's an easy one because E is just right after D, so that's a 1. But that one tells us there's a 16. So now we have 16 plus 8, and that's 24. Yep, go ahead.
If you're comparing 3DC to 3F4, you can just look at like the second digit, the D and F, and say from D to F is 32
Yep.
bits, and then
You can do that too.
subtract from there down to 4 to
Yep.
C.
Yep, exactly. You can borrow all the tricks from base 10 subtraction. But the bottom line is there are 24 bytes between those two. Okay, so now we got the first mystery solved. The second mystery is, what is the index I need to use when I index into array A to quote unquote accidentally get to X? In other words, how many elements of 4-byte integers can I fit in 24 bytes? 6 of them. Very good. Okay, so I can actually do it now inside Gdb, because guess what? I can do, well, since it's 6 elements, that means we need A bracket 6. Because we are looking at how many elements are between the beginning of A and the variable that we want to overwrite. So that means the variable that we want to overwrite becomes the 7th element, not the 6th. Okay, as the 7th element, it has an index of 6 because we count from 0. Well, let's double check first. What is X supposed to be at this point? 42. And what do we get? 42. Okay, so in Gdb, I can now set up the experiment and say set var A bracket 6 equals to, let's turn it into something else, 71. Okay, single step the program, so go back to main. This is return 0 from main itself. Print X, guess what? X is now changed to 71. Now, granted, I just cheated, okay? Because I used Gdb to figure out the addresses first, and then I do the math in order to find out what is the exact index I need in order to overwrite local variable X. So now that I know the numbers, okay, I can now go back to the source code of the program and do it in the source code instead. So I was off by 2, A bracket 6. And this time, well, I think most of you know what's going to happen this time. Okay, let me turn on the line numbers. Okay, so the bottom line is I just doctored this program so that line 5 is going to override local variable x of main. But as I said, this one is handcrafted. Okay, you guys saw how I handcrafted this program. Does it mean that it is not possible to happen if I'm not handcrafting something like this?
No.
It's entirely possible, right? Because if you use an array to go through quote unquote array A, and somehow in your calculation or the variable that controls the element is not controlled properly, you can still end up with something like this. But when you look at the symptom, what's wrong with this program? It's not crashing. F itself is not misbehaving. And who is misbehaving? Or who is going to misbehave because of this problem? Main. Okay? Now, if you think this is bad enough, let's think about something that's even worse. Okay? Because what can happen here? Remember recursion? Where you can have one function calling another function calling another function and so on. So let's not even think about recursion. Let's say main calls f, f calls g, g calls h, h calls I, okay, and so on. Let's say just I here. I has a problem. I says, a bracket something equals something, but that turns out to be something that's really far away from the end of the actual array. So I can overwrite variables in h, it can overwrite variables in g, it can overwrite variables in f, it can overwrite variables in main itself. So by the time you realize there's a problem, you'll be so far away from the actual point when memory is actually overwritten. Do you guys kind of see the point?
Yeah.
Okay? Yep, go ahead.
So as long as, like, if you change that 6 to, say, 3, then it's all good because it's in the array.
There turns out to be some gaps in memory that the compiler says, okay, we'll leave some gaps. That's only for performance purposes. So for performance purposes, I think everything is aligned by 16 bytes. So the entire, well, I shouldn't use the word frame, but you guys know the word frame already, right? So basically all the frames, they have to be on a 16-byte boundary in order to maximize performance. So there turns out to be some places where you can actually overwrite without destroying stuff.
Alright, and then this one, logically you made it to only be able to store 2 variables, but it could hold, oh, it just counts from 1, not 0 when you make an array?
Which one?
Not array, like its maximum intended capacity, wouldn't it go, you have a variable at A0 and A1?
Nope, in this case there's only a bracket 0 because we say A is an array of one element.
Oh, okay.
So with only one element, you only have a first element which has an index of 0.
Okay, so this one actually counts from 1 upwards, not 0 upwards.
No, it comes from 0. I think I might have misunderstood your question.
Because I'm looking at it like actually just setting up an array because that's the part I got caught on. Like in VB, if you declare an array and you put size 6, it can store 7 things inside of it.
Really? So this is different. This is different. In C and C++, when you declare the variable, this is telling you how many items you can store.
Okay.
But because everything has to count from 0, that means you can only use index 0. 0 is the valid index into this array. That's the only thing.
Oh. Okay.
Okay, that's a good question. Yeah, that is a very good question because I guess in that case, Visual Basic let you specify the index of the last element, but in C and C++, it wants you to specify the number of items in the array. That's the difference. That's why it's off by 1.
Alright.
Okay, very good. Yep.
So if you have a recursive function inside main, and then the OS is allocating memory to it, so it would be allocating memory like...
It's not the OS. The OS only allocates stuff that is static, that it does not change over time. But when we talk about local variables, up to this point they're all auto local variables. The operating system is not responsible to allocate that. The program itself is.
How does it know how much memory it's going to take for a recursive function though?
It's still on a per invocation basis. So when you call, then it allocates. When you call, then it allocates.
Yep.
So it never really needs to know how many to allocate at one single time, because when you call again, then it allocates.
Okay, I guess the thing that's messing me up is that when you're mentioning like how you had your main function FGHI example,
Mm-hmm.
if those were all like instances of one recursive function,
Yeah.
like they would still all be contiguous in memory. even
Yes.
if-
The frames would be.
Okay.
Mm-hmm.
Unless it can still overwrite.
Yeah. Oh yeah.
How does it know like to make? I guess like how does it know to make them? Okay. Yeah, sorry, because arrays are static sizes. So.
Right. And that's why they are static. Because they're allocated in the same chunk of memory as all other variables, and that cannot change dynamically. All right. Are there any questions at this point? Because we have gone through, some interesting ways to crash a program, but are there any questions? Yep, go ahead.
I've seen you typing the semicolon G++. I didn't understand that command.
Semicolon G++.
Yeah, exclamation mark.
Oh, the exclamation point is a shortcut. So in Bash, when you say exclamation point something, you're basically you're telling Bash to repeat the closest, the most recently used command that starts with the same beginning letters. So when I say exclamation point G++, I'm saying, okay, Bash, go ahead and repeat the most recent command that starts with G++. So it's a quick and easy way to, not having to retype the entire thing, you just retrieve it. Okay. Yep, go ahead.
I'm just curious in terms of interesting ways to crash something. If you had a if you had a program that accidentally overwrites the return address to kind of be the function that was overwriting the return address, would it just go into an infinite loop without
Yes,
giving
it
a
would.
fault?
Yep.
But would it not even give a fault? It would just like hard crash like the entire program? Or?
No, it would not. It would not be consuming any more memory because you are continuing. Let's see. Yeah, in fact, it will. Because it's the same thing as an infinite recursion.
Yeah, but it wouldn't.
Let's make that happen. Do you guys want to see that happen here, based on what he said? Okay. Okay. So, what we have seen at this point is some memory in the memory space is used as a return address. In other words, those are the locations where your function knows, oh, when I'm done, I need to continue execution at blah, 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 blah. Okay? That's something that we know already. And we also know that we can overwrite just about any location by abusing array indexing. Okay? That's something that we also know that we have seen today. In fact, we know that a bracket 2 is exactly referring to the location of the return address. So the question now is, can we change the right-hand side of this assignment so that we overwrite a bracket 2, which is the return address, to exactly the starting point of f, which means function f will quote-unquote return to function f, which basically means it will keep allocating more memory until there's nothing left. Is that okay? Yeah. Okay, so the answer is yes, we can do it, but we cannot just do it like this. Okay? We cannot do it like this either because f is a function. And not only that, f does not return an integer either. Okay, so it will have a type mismatch issue. And every time you have a type mismatch issue, how do you resolve that? How do you brute force the compiler to do what you want to do? Typecast it, exactly. So we just say, well, even though %f refers to the address of a function that returns void, which has nothing to do with integer, you know what? Treat it as an integer. And obviously, this is a very, very bad thing, okay? But that's the whole nature of C and C++. It is not an instructional programming language. It is a programming language designed by a guru for himself. Okay? So we are looking at a circular saw or a chainsaw that has no safety features whatsoever, but it does have maximum performance. If it cuts through something, it cuts through very quickly. All right, so let's go ahead and see what happens when this program runs, okay? Because I'm speculating this will get into an infinite loop, but it will chew up memory, okay? And we will eventually crash because it runs out of memory, okay? So we'll recompile the program, and just let it crash. Segmentation fault, very good. But does it crash because it runs out of memory? That's the question. Run the program, and it says here a bracket 2 blah 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 is causing an issue, and this part is a little bit out of the scope of this class, but I can at least do this. Okay, I can say where's the address of A, and it says it's BFFF8. That's a higher address. Oh, it's actually undoing stuff. It's not chewing more memory. It is actually it keeps returning. It's undoing stuff to the point where it is it cannot access the location anymore. This will be clear in CISP310. Okay, in CISP310 we can definitely explain the behavior. Yep.
Is a infinite recursion considered a hard crash or a soft crash?
When it does run out, it's a hard crash, because when it does run out of memory, it will cause a segmentation fault, and at that point there's no way to recover, and as a result it's still a pretty hard crash. Now there are hard crashes and there are really hard crashes. If in Windows, if you get the blue screen of death, that is like really hard crash, right? Because there's no way, even the operating system itself is gone. And in an application you have, I don't know what is considered a soft crash, but any crash means it's not recoverable. Your program just stopped working altogether. It's gone. Now you can probably have programs that have infinite loops, which means it just hung up on you. Okay, you click on something, it starts working, but it never comes back. Okay, so but that's not really a crash. It's just your program not responding anymore. So are there any questions about all of the stuff that we have seen today? Okay. Are there any disagreement that C++ may not be the best programming language for a class like this? But that part I have no control over, okay? As much as I agree with you that C and C++ gives you too many flexibility, okay, and not enough checkpoints and not enough checking to cause programs to crash in mysterious ways, they do, okay? But I would much rather introduce those problems today so that when your program crashes, oh, okay, maybe I abused an array, maybe I was accessing an array out of bound. But if I don't talk about it at all, when your program do crash, what are you going to do? Where do you start to debug your program? You would have no idea. I did not. Okay, so that's the end of today's lecture, but I do want you guys to kind of read the topics on arrays, because we are actually moving on to arrays at this point. So I do want you guys to continue your reading on arrays, and then on Wednesday, we'll start to have a homework assignment using arrays. Yep, go ahead.
Even though
Oh, sorry, go ahead. And then
There's no class Wednesday.
oh, there's no class on Wednesday. Yes, so I'll see you guys on next Monday. Have a nice weekend. That just sounds so odd. It's Monday and I say, have a nice weekend. Yeah, go ahead.
even though memory is kind of allocated right to left, are the binary digits still stored left to right?